here's a coffee cup on the table, and if I put the hot coffee cup onto the cold table, okay, and I come back after a long time, the hot coffee cup is room temperature, and the room is just a little bit warmer. So if it's an insulated room, the temperature of the room rises. It's like a calorimetry problem, right? They come into equilibrium, and that means that the heat will have flowed out of the hot coffee into the warm room, and there are 4 different ways that the coffee can cool down, and the simplest one is conduction, okay? And if you think about it, the coffee cup is going to conduct to 2 different places. It's going to conduct to the air. It's going to conduct to the table, right? Let's just look at the table. If we look at the table, aren't the atoms in general of the coffee cup going faster on average than the atoms of the table? This is to say that the table is cooler than the coffee cup, right? Here's the coffee cup, here's the table. Yeah? Yeah, are you picturing that? Right? Now watch what happens when the hot molecules of the, I'm trying to do it sideways, right? Hot molecules of the, right? Hot molecules of the, it's all over. Okay. Watch what happens when the hot molecules of the coffee cup come in contact with the cold molecules of the table. Are you ready? Are you ready for this? Watch. Right? Then it's like, then they're both going about the same speed, yes, aren't they? This is a patented demonstration, yeah? Okay? Let's watch it again. Let's watch it again, right? Here is, I'm trying to, yeah, there we go, right? Here's the hot coffee cup. Here's the cold table. Well, watch. See how it like gets it going faster and faster until they're all going about on the average as fast. That's a, okay. There we go. Right? It's also doing the same thing to the air. It's warming up the air, okay? So conduction is heat transfer by contact and random wiggling, right? Okay, so it's the, literally it's the molecule banging into the molecule next to it that sends the thing on down the line, right? It's not a wave. It travels very slowly. Heat conducts very gradually through things, although, you know, some things it conducts pretty fast through. The best demonstration I've seen of this is you can take 2 rods, one made of copper, one made of stainless steel, right? And you have somebody hold two volunteers up there, get a blowtorch, right? You can get the stainless steel rod glowing red hot on one end, and the other person's holding onto the other end, this long, yeah? The copper rod, you just take the torch and start going like this on the other end, and in a few seconds the person's like, ow, 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 and they've got to drop it, right? So copper conducts heat like crazy. Stainless steel conducts heat really pretty slowly. It's amazing that they're both metals, right? That's why in revereware pots that are stainless steel for convenience, what's the bottom made out of? Copper. It's copper clad, right? So that it conducts the heat a little better, right? Okay. Heat goes from hot to cold, and this is really just sort of an averaging thing, right? On the average, basically, you just take the average, the weighted average, and heat will have flowed from hot to cold in any calorimetry problem, yes? If you go to some average temperature, the cold stuff gets the heat from the hot stuff, right? Kind of a thing, okay? And the flow rate, and we don't really have this formula anymore, but it depends on the difference in temperature. It also depends on the area, so the bigger the area, the faster it flows. The bigger the temperature difference, the faster it flows. This is why you feel cold on a cold day. Faster, right? Depends on the material. So are you insulating with copper? Not so good, right? Are you insulating with down with feathers? Better. Yeah, okay. And then it also depends on 1 over the thickness. So the thicker it is, the more slowly heat flows, right? Okay. And I have a simulation of this that I'll show you here. Insulation prevents conduction, okay? And you can insulate with down stuff and with synthetics. Let me get, and we can talk about the thickness, right? Thicker things tend to insulate a bit better, right? I've got the greatest demonstration of this, though. I bought these guys. Here are 2 objects. I've got this one and this one. They're obviously not the same material, are they? Which one's going to conduct heat better? Yeah, it's like, oh, there we go, right? One of them's made of metal, right? This one's made of non-metal, polystyrene. I'll be right back. Oh my God. You guys, you tricksters. Whoa. You should have switched these, right? Okay. Dang it. Okay. This is kind of fun. I'll put these guys on there. A couple chunks of ice. And then, you have to do this thing like, oh, they're the same material, but maybe they're not, right? Holy cow. Holy.
It's melting too fast.
It's crazy, yeah. Yeah, one of them is obviously melting a little faster than the other one. In fact, this one has not yet begun to melt. This one is like a third melted. This is an amazing thing. I did not heat that thing up before I put it on there, right? That's got to be some exotic metal, yes? Doesn't it? I was like, when I saw this demonstration, I was like, what is that made of? It's made of aluminium. That one's aluminium. This one is styrofoam painted black. You know styrofoam comes in like all sorts of densities. Like they put it in the walls of houses. Blue block you can like build coolers out of and stuff, right? Yeah, there we go. It's about to drip, but that's okay. All right. Let's see. Start the radiation demo. Okay, let's watch the hot water. Look for the brown. Brown. Looking for it. Not seeing it. There. Was it there?
No.
Was it earlier? I don't know. We have hot water now. Yeah, it's not going to do it for us. We already have the hot water. Okay, so I'm going to fill these guys up. One of them is just the ordinary silver color of the tin or the steel it's made out of, and this one has been painted with a special black paint. Okay, and so the question is, which of these is going to cool down faster? What do you think?
Metal.
This guy will cool down faster than this guy, because this has got paint on it. This guy doesn't have paint on it. This seems like a real. Whoa, baby! Bad faucet. They've been messing with it, so we just got an air bubble through there, right? Okay. Ow. This is like, I don't think that's an acceptable. Okay, I've got the same amount of stuff in there. Let's stick the caps on them. Let's stick, this will be the black one will be 2, the silver one will be 1. Okay. Escape. Let's go to Logger Pro. And there's the temperature. That's pretty hot, so let's hit collect. Okay, let's go back to our heat transfer demonstration. Let's minimize this. Okay. And then I've got a simulation, so let me show you my simulation of heat transfer. Okay. I don't know if you guys can see it. Where is there somebody that says C? There it is. Hello, I'm clicking twice. Okay. I think this is it. There we go. I love that. Let's go to the full screen. Can you go to the whole screen, please?
No.
Okay. And then it says something that looks like it's going to do this forever, but it never does. Okay, this is the matrix, right? It's like, whoa, there we have it, right? Everything here has a heat of 2 or temperature of 2. In fact, it's very orderly. This one has, everything has a temperature of 8. Yes? Okay. If I hit the space bar, what it does is it rolls a dice, and a 2 and a 2 becomes a 3 and a 1. So on the microscopic level, energy is conserved. Do you see that? Isn't that right? 2 and a 2 adds up to 3 and 1. Total kinetic energy is the same, right? Hit the space bar again. Again, we just became a 1 and a 3.